Hello, this is my 16-bit Minecraft computer based on the LC-3 instruction set architecture. This architecture is from a textbook which I will cite in the description. This design uses a simplified version of the ISA. The architecture uses a 2's complement number system. It currently does not have any input or output systems, as my goal was only to build a functioning processor. I did not do a good job of laying it out before I started building, so it is very large and therefore very slow. Also, just ignore the things at the horizon. Those are prototypes for this design. The ISA uses 8 16-bit registers in the register file. Each register has an enable signal which controls if it is written to. This is the decoder. It determines which register to write to based on an enable signal and a few bits from the instruction. The white wall is the bus which connects many of the components. It serves as the data input for the registers. All the registers output into this tangled mess, which leads to 32 8-to-1 multiplexers, or muxes. There needs to be 32 since there must be 2 possible outputs and each output is 16 bits. The lime green is the primary output value, the blue is the secondary value. They're independently selected by the muxes. The secondary output of the register file then goes to another set of muxes. This selects between an immediate value that is encoded in the instruction or the secondary register file output. The immediate value is sign extended since it's only 6 bits long. A bit from the instruction controls which of these two is selected. The output of this mux, along with the primary register file output, is then sent to the arithmetic logic unit, or ALU. The core of the ALU is a ripple carry adder. The adder design is based off a design which I'll link in the description. The ALU can perform add, and, not, and pass through operations. A control signal selects which of these outputs should be used. This piston selects between inversion and pass through. The AND operation is done down here. The rest of the system is the ripple carry adder. A carryout term is generated and passed to the next module. The operations are performed for each bit. The output is then selected and passed to the orange wall line. The ALU output eventually meets the bus, the white wall. There are 4 possible bus inputs. Instead of using a mux, each signal has its own control, which is just necessitated by the layout of the design. Since there are 4 signals, there needs to be a 2-bit control signal, so there are 2 pistons. The green, purple, and light blue are the other bus inputs. If the instruction is an ALU operation, the data will then go through the bus all the way back to the register file, where the destination register will be overwritten. Besides the data path, another key element of a processor is the control signal. The LC-3 architecture uses a program counter, or PC register, to store the memory location of the next instruction. This register is identical to those used in the register file. One thing I forgot to mention earlier is that many of the lines have this sort of piston contraption. This is because the finite state machine is prone to causing glitches. While these should not be an issue because this is synchronous logic, the short bursts can cause the pistons to drop their blocks, so I need to smooth out the signal. All the registers work on the rising edge of the clock signal. The output from the PC register goes to 2 places. It branches back around to the incrementation circuit. First, there's a mux that selects between the PC signal and the primary register file output. The register file output is used for a special type of load and store operations which are not implemented with the current finite state machine. The output of this is then sent to another Ripple carryout where it is added with a constant value from the instruction data. A mux selects which bits from the instruction are used as different operations use a different number of bits. Underneath this adder is another adder. This, however, only has one input per bit. It always takes the PC value and adds 1 to it. This is the default incrementation. A mux selects which incrementation method is used, and then the output is sent back to the PC. The output from the first adder can be sent to the bus for the previously mentioned unimplemented special load and store operations. The output from the PC can also be sent to the bus. If the processor is fetching an instruction, the data from the PC is sent through the bus to this register. This is the memory address register, or MAR. The MAR stores the address of the memory location to be accessed. I implemented 64 memory addresses. As such, I only used the 6 least significant bits from the MAR, as that allows for 64 unique addresses. The 6 bits from the MAR are sent to the memory decoder. This determines which memory address to access. This huge thing determines 64 unique signals based on the 6-bit input. Only one output is active at a time. Each output goes to one memory location. The first 32 addresses, those numbered 0 to 31, are read-only. The processor cannot write any data to them. I implemented them this way to make it easier to program, as I can just flip switches to reprogram it. Again, the control signals need to be smoothed to prevent issues. The read-only memory is very simple. The enable signal triggers a piston which allows the data to be sent to the output. The next 32 addresses are writable. They receive an enable signal and a read-write signal, which determines the performed operation. The green roll is the input and the brown roll is the output. The enable signal causes 2 pistons to move, allowing for the memory address to output, as well as potentially allowing it to be overwritten. This long red roll line is the read-write signal, while the others are the enable signals. The data output goes to a mux. This mux selects between the value in the bus, the pink wall, and the memory output. This is because it leads into the memory data register, or MDR, which stores both the output from the memory as well as storing anything that is going to be written into the memory. This mux selects depending on if the operation is a load or a store. The MDR then stores the selected value. The value is sent both to the write line from memory as well as potentially to the bus. If loading data, the value is then sent to the register file. If the processor is loading an instruction, the value is sent to the instruction register, or IR. This stores the current instruction. The yellow roll is the value of the current instruction. Some of the bits from the instruction are sent to the finite state machine, while others are sent elsewhere. In order for branch instructions to work, there must be a way to determine which branch to take. The LC-3 ISA does this based on the last value written to the register file. It has 3 condition bits, negative, 0, and positive. Note that my labels for the positive and negative are switched. My bad when designing this. Each bit is only written when the registers are written over. To test for 0, all of the bits combine to a single signal. If it is 1, then the total number must not be 0. For negative bits, the most significant bit is checked. Since the processor uses 2's complement numbers, the most significant bit being 1 means that the number is negative. If neither of these conditions are true, then the number must be positive. 3 bits from the current instruction encode which bits to check. If any of the conditions match, the branch enable signal is triggered. The next state logic for the finite state machine takes the current state, the operation, and the branch enable signal, and then uses those to determine the next state. The current state is stored in these registers. The enable is always on, since they overwrite each time. The state is then sent to the next state logic as well as the control logic. The control logic determines the signals that control the operation of the entire processor. It uses the current state to determine what the rest of the system must do. All of these logic systems use the same basic idea. It is a simple way I found to implement Boolean algebra in Minecraft. One of these signals acts as the primary signal. It can be inverted or just passed on, or could even just not connect if the sum of product term does not use it. For all of the other inputs, the pistons are either set up so that they are either on by default, off by default, or don't exist. This allows for inverted signals in sum of product terms to be easily implemented. Additionally, the instruction outputs often act as control signals for various components. This is the case with the destination register selection. The register file muxes also use bits from the instruction as control. A mux selects which bits to use to select the register file primary output. The secondary output selection is simpler, as the same 3 bits always correspond to it. The final elements are the clock and reset signals. All the registers take these as inputs. The reset is just a simple lever. Additionally, these lamps represent the current state of the finite state machine, as it is easier to follow that way. Since I did not plan out the placement of all the components before I started, the design grew very large. As such, the clock needs to have a very large time period. These repeaters are only half of it, as they lead into a T flip-flop, which provides a square wave for the clock. This lever allows me to engage and disengage the clock. This is useful in debugging, as I could use it to pause the processor. While it was fun making this, I don't think I'm going to build another, as it took a ton of time. If I were to, I would try to make it a lot faster. I would spend more time planning the layout beforehand. I would also try to make a pipelined processor so it could operate faster. I would also use a slightly different architecture, which would facilitate the pipelining.